Hi there. As part of this video, as part of this video, we would be going through a project topic for machine learning as part of the course Machine Learning Foundations for Product Managers. So here the problem statement is that combined cycle power plant uh, is the power plant which comprises of gas turbines, steam turbines, and some other steam generators as well. And there we have to predict the hourly energy, electrical energy output, which is dependent upon the variables temperature, pressure, humidity, and vacuum. So we have a data set here which consists of 9568 observations, and we have these following features which exists. So we since this is a structured data, so we'll and it is a supervised learning, we'll follow two models here. One is the multiple linear regression and the other is the decision tree. So multiple linear regression here, as we know that it is a simplistic model, and in this model we will divide the whole data into two parts, which is the training data and the test or the validation data. So training data we have this divided as 90% of the overall data. So first 8499 rows have been copied and divided here as part of this worksheet as CCPP train. And the validation data is the rest 10% of it, which is roughly around 10 to 11%, which is the 1069 records which have been divided. So we'll apply the multiple linear regression using the Excel. So if we apply the linear regression using the Excel, then we come up with the following results here. So if we see the adjusted R square, so this adjusted R square is coming to close to 1, right? So which explains that 92.8% of variance of dependent variables, that is this predicted electricity which we are predicting, can be explained by the independent variables AT, V, AP, and RH, the temperature, vacuum, pressure, and relative humidity. Also, if we see the significance F and significance P here, so significance F is coming out to be 0, so which is telling that this model is statistically significant. So which means that if we this model is absolutely applicable here, uh, and it is giving a it is fitting the features well. So even the web parameters ATV, APRH, if we see all these features are applicable and contributing well to the prediction, the answer is true. Because if we see the p value, which is coming very close to zero, or I mean this is zero and this is exponential to the power of minus 191 and further. So which again allows us to reject the null hypothesis that they are not influencing the final predicted value, which is the PE. So so this, if we then calculate and measure the accuracy of the model using multiple square error, which is actually the square root of the difference between the predicted value and the actual value. So this is the difference between the this is the difference between the this is the predicted value which we are calculating using multiple linear regression. If we simply see the definition would be 80 into the actual value, then plus v, the coefficient, into the actual value of v, and then the coefficient 0.066 into the actual value of AP, and then the coefficient to the particular value of RH. That is how, and plus the intercept which we'll add. So if this is what is being written here in the formula here, so this is the predicted value which is coming from the linear regression model, and this is how the predicted against each observation is calculated. And finally we see the error between the predicted and the actual value, which is the difference between the predicted and the actual. So we calculate predicted and actual for each row, for each observation, and then we also calculate the absolute value, the which is the absolute error for this. So if we see two accuracy metrics, which is mean square error, so we have just squared the each observation G2 and G10 till G1070, and we have divided by the overall count. So this is giving us a mean square error of 29.66 and mean absolute error, which is also the which is the sum of these value divided by the count, which gives us the average. So it is mean absolute error. So this mean absolute error is coming 3.63 and 2.96. So this is coming, I mean, these should be as less as possible. So this is telling that the model, I mean, these are not absolutely, I mean, very close to zero or so, but these are fairly fine. So it seems that the model is doing well here. Now we have assumed that this is all, linear relationship, and hence we have used multiple linear regression. But it could be possible that maybe some variables in some way are, I mean, not linear, non-linear itself. So we'll also try the decision tree model here on the same data, and then we will see that what the output is coming in. So if you go to the decision tree, so in the decision tree, what we have used is we have tried to use Python as a code here. So we can embed the Python code here in the Excel. So on the overall DFCCP train data frame, we have just taken the populated the frame with the CCP train worksheet, which is the Excel. So we have imported pandas and we have used this. So if we see the DCCCP train info, which is the data frame info as part of C2, so if we just go down here, so let me clean and rerun it, that would be better. So we are just rerunning it. I'm pressing Control plus Enter to rerun it. Yeah. So now if we start from bottom, so we see 8499 entries have been there, and all the entries, I mean, all the particular features with all the observation have been loaded into this data frame. So then what we do is we divide it into train and test data. So we take the train and we simply use ilog function, and we split the first four columns and we put it into X train. And similarly, we use the Y train and we split it into and the last column which we take as the Y train info. Similarly, we load the test data using the CCPP test worksheet, and then we use similarly the ilog function and split it into two parts, which is the first four columns in the test. Sorry, first in the test info, in the test data frame X test, and in the Y test we give the predicted value which we need to predict. So how it comes is, if you see the C2 cell, this is 8498. If you see the C3 cell, which is the train data, it is coming as 8499. Oh, sorry, the C4 cell. So if you see the train data which has been, the test data which has been loaded, which is the C4 cell, so it is coming as 1069, and the train data is 8499, right? So finally, we see the C5 cell where we create the X test and the Y test. So X test we have the first four columns, and in the Y test we have the only the last column. So then we use sklearn tree import function for the decision tree regressor class. And here we are using these hyperparameters. We have used square error for now. We use the maximum depth as 5. It is easier to visualize. Decision trees are difficult to interpret. And although the linear regression is simple to interpret, we use a minimum sample split parameter of 100. So, I mean, it would keep on splitting till depth of 5, or minimum samples which are needed for splitting is at least 100. If we don't give this, it will split it up to the purest value, so which would enable the tree to grow very large, and we keep the random state as 5. So once we have the decision tree, we fit the train data, X train and the Y train, into it, and we get the final decision tree regressor which has been populated now. So once the ML has been trained, what we do is we use our X test, which we have populated from the X test data, CCP test, to predict. And we populate it into a data frame called Y predict. So this Y predict is, I mean, I have just used uh, the the Python Excel values instead of the object, just to show you that these are getting predicted here, right? So all these are getting predicted here. So this is the list, which is the list populated here. Finally, I have used matplotlib to just plot the tree just for visualization purpose. So if we see, I mean, we can click in here, and it will, if we can see that, this is the tree, this is how it is being splitted. Sorry, it is not coming in fully, but this is how it is splitted. So x0 is the first feature, which is our 80. So it has defined, it found out a point for a split, which is 17.815. So this is coming with an algorithm. So decision tree uses something called as Gini, or Gini and entropy, which are measures of purity and impurity. So I mean, it uses its algorithm and is split it such that x0 is less than 17. So data sets rest, all the observations are going here, and list all the samples are going here. Then similarly from x0 less than 22, it is using x1, which is the next value. So this is coming up with deciding which features it has to use and how the split has to be created. So that algorithm, it is an inbuilt using Gini and entropy. There's no time to go into that. But finally, how do we compare it? Is that if we see, I have printed the. I'll just close this pic so that we can see MSc and MAE as well. So this is the pic. I mean, I let me move it down. So yeah, so I have calculated MSc. So I have used metrics, import mean squared and mean absolute error. So we have calculated the mean squared error, which is coming out to be 18.725, and decision tree as the mean absolute error is 3.458. So if we just compare it, I mean, it is coming better than the linear regression model. So, I mean, we can't do much interpretation on the linear regression, on the decision tree as such, that how split. By these values, it seems that decision tree is a better model. But although if we use stats and see, it seems, all the variables are dependent and seems to be linear related, and we are getting a good, 92% of variance of the dependent variable, right, over the independent variable. So that is how, I mean, it seems both the models are fairly doing well and reasonably fitted well. Okay, so that is how we see. And if we just, if we just try out and want to see the, if we change the hyper parameters, and we can see how the mean square error and absolute error is is are changing. If we change the max depth to 10, if we I mean have more depths, how it is faring. So it is 18, 18.7 and 3.5, right? If we just press control enter and run it, yeah, it is running. It will take some time because it's the depth is 10, so it will take more time to load here. Give me a few seconds, let it complete the operation. All these operation are running on the Microsoft server. The image is getting generated. So our MSc and MA is being calculated after these operations. So hence, if this operation has to complete first, only then we'll get the MSc and ME. Yeah, so it is there. So see, if we see the MSc has improved to 15.3 and MA is also has improved to 2.989. So with more depth, we are getting a better MSc and MAE. Now it is up to us that, I mean, we want a balance between the compute power and our model accuracy. So we can keep a balance between two. So that is all. I hope this explanation is good enough to explain both the models and how we handle the problem for the prediction of the PE. Thank you.